Hello everyone, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to discuss the topic Electromagnetics, Lecture 7, in continuation to the last 6 lecture. This is BSc Physics 5th semester paper Electromagnetic Theory, Unit 2 syllabus. The contents of the present lecture are Introduction, Magnetic Induction Field Strength, Properties of Magnetic Induction Field Strength. Then after, Divergence of Magnetic Induction Field Strength and its importance. After that, we will have the discussion of curl of magnetic induction field strength and its significance. Next, proving that del bar dot b bar equals to 0 using Boit-Savart's law. Lastly, comparison between electrostatic field and magnetic field and summary. So what is the magnetic field? In the last classes, we have the detailed discussion that the space around the magnet in which its influence is felt is called magnetic field. In the magnetic field, when we keep the unit north pole at any point, that can experience the force. That force is called magnetic induction or magnetic induction field strength or the intensity of magnetic field strength at that point. So therefore, we define magnetic induction field strength B as the force experienced by a unit north pole placed at any point in the magnetic field is called as magnetic field strength or magnetic induction at that field. Suppose if you keep the magnetic pole of strength M in the magnetic field of induction capital B, that will experience the force F is equal to M into B. From this you can write B equal FB by M, right? In this, if M equal to 1, then B equal to FB. In general, to define the magnetic field strength, we use the unit north pole as the reference, as like unit positive charge in the case of electric field strength. Therefore, so the force experienced by a unit north pole placed at any point in the magnetic field is called as magnetic induction field strength at that point. So magnetic induction denoted with the letter B bar. It is a vector quantity. Its direction is along the direction of the force acting on the unit north pole. Okay. Now, the SI unit for B are Weber per meter square, Tesla, Newton per ampere meter. Tesla is the biggest unit. Gauss is the smallest unit. It is the CGS unit. 1 Tesla equal 10 power 4 Gauss. From that, you can write 1 Gauss is equal 10 power minus 4 Tesla. Okay. So these units you can write from the different formulas we have for the magnetic induction field strength. We will see later on. Here B value depends on nature of the medium. But we have, apart from B, another physical quantity H bar. H bar is magnetizing field strength. It is independent of nature of the medium. Here B and H are related as B is equal mu naught into H plus I in SI system. But in the case of free space or vacuum, intensity of magnetization I is equals to 0. Then you will get B equal mu naught into H. So I will extend the concept here. When the magnetized material is kept in the external magnetic field, that material can be magnetized, that we convert into the magnet. The magnetic moment induced in that magnetic material per unit volume is nothing but intensity of magnetization. Our magnetic pole strength per unit cross-sectional area is called as intensity of magnetization. Here I value depends on same nature of the medium. So both H and I doesn't depend on nature of the medium. They have the same units, ampere per meter. Okay. So in the free space or vacuum, in that case, since I equals to 0, we get B equal to mu naught into H. Therefore, magnetic induction field strength is equal mu naught times to the magnetizing field strength H. If you take the CGS system, the relation between BHIR, B equal mu naught into H plus 4 pi I, right? Here, when you substitute I equals to 0, then B equal to mu naught into H. Okay. So, magnetic induction field strength or field vector is a vector quantity. It is measured in the units Weber per meter square or Tesla or Newton per ampere meter, or CGS unit is Gauss. 1 Tesla equal to 10 power 4 Gauss. Right. You can define the magnetic induction field in another terms. We know that when the charged particle Q is moving with velocity v bar in the uniform magnetic field of induction v bar, then that will experience the force F bar equal to Q into v bar cross v bar. If you take the magnitude, you can write F equal Q V B sine theta, right? So from this you write B equal FB by Q naught V sine theta. Okay, here FB stands for the force experienced by the charged particle. Q naught is the charge of that charged particle. V sine theta, velocity component perpendicular to the field direction. Okay, when the charge is moving in the uniform magnetic field at an angle theta, its velocity has two components. Velocity component parallel to the field direction v cos theta, perpendicular to the field direction v sin theta. So from this, it is the ratio of FB to the product of Q naught and v sin theta. So how we define B? The ratio of the force experienced by the charged particle or charge to the product of charge and velocity component perpendicular to the field direction is nothing but magnetic induction field strength or the intensity of magnetic field of induction. Okay. From this, what is the SI unit of force? Newton. By charge, SI unit Coulomb. Velocity meter per second. Velocity meter per second. So here Newton, charge dimensional formula A into T, velocity dimensional formula L by T. Here T cancellation, then A into T. That equal A into T. So then you will get the unit Newton per ampere meter. So dimensionally you can check that. It is also defined in other terms, in terms of magnetic lines of force. The total magnetic lines of force crossing normally through given surface area is called magnetic flux. Magnetic flux is a scalar quantity. It is measured in the units Weber. The number of magnetic lines of force crossing normally through unit surface area in the magnetic field is called as flux density. Magnetic flux density. So therefore, we are writing flux density B equal the total flux by area of the given surface. So what is the SI unit for flux? Weber, Weber per meter square. Hence from this we are writing the unit for B as Weber per meter square. Okay. So B is defined as the number of magnetic lines of force crossing perpendicularly through a unit surface area is called as magnetic flux density. Right. Now, we know that when the current carrying conductor of length L carrying the current I is kept in the uniform magnetic field of induction capital B, then the conductor will experience the force FB called ILB sine theta. Vectorially, you can write it as FB bar equal I into L bar cross B bar. Okay. So from this, when theta equal to 90 degrees, so maximum force exists, FB equal ILB. From that, you can write B equal FB by IL. So from this, how we define, it is a ratio of the force to product of current and length of the conductor. Right, when it is possible, when the conductor is kept at right angles to the field direction. Right, so therefore, The magnetic induction field strength can be defined in terms of current carrying conductor as it is the ratio of the force experienced by the current carrying conductor when placed perpendicular to the magnetic field to the product of current and length of the conductor is called as magnetic induction field strength. So in this you substitute the units SI unit per force Newton by current unit ampere, length unit meter. So Newton per ampere meter, we are writing the unit for B from this formula. Okay. So one more property of the B, Gauss law in magnetism states that the magnetic lines of force or the magnetic flux emitting out perpendicular to the closed Gaussian surface is always zero. So integration method we write here phi B magnetic flux through the closed Gaussian surface, that is closed integral B bar dot ds bar equals to 0. So this is the Gauss law in magnetostatics. Already we studied in electrostatics Gauss law. What is that? The electric flux through a closed surface, that is closed integral E bar dot ds bar equal to 1 by epsilon naught times to the charge enclosed by that surface, Q by epsilon naught, we are writing right side. But in the case of magnetism, this formula we express as closed integral B bar dot ds bar equals to 0. So what is the physical meaning of that? Since the magnetic lines of force are always closed curves, the net magnetic flux over a surface is always 0. That means isolated magnetic poles do not exist in nature. Always the magnetic poles exist in pairs. Magnetic poles always exist as the pairs. So isolated or individual magnetic poles do not exist in the nature. This is the physical meaning of Gauss law in magnetostatics. Okay. So we write it as del bar dot B bar equals to 0. Closed integral B bar dot ds bar equals to 0. In differential form, you can write it as del bar dot B bar equals to 0. That means the divergence of magnetic induction field strength is always 0. Its physical meaning is that monopoles do not exist in nature. Always the magnetic poles exist as the pairs, or the magnetic lines of force are always closed curves. But whereas the electric lines of force are the open curves, because there the electric flux through any Gaussian surface, closed integral E bar dot ds bar equal, we are taking Q by epsilon naught. But in the case of magnetism, closed integral B bar dot ds bar equals to 0. You remember that. For the steady currents, the curl of B bar, that is del bar cross B bar equal mu naught times to the current density. Del bar cross B bar or curl B bar equal mu naught to J. So these are the properties. Del bar dot B bar equals to 0 is always del bar cross B bar equals to 0, or del bar cross B bar equal to mu naught into J bar for the steady currents. Okay. For varying currents, del bar cross B bar not equal to mu naught J, there that formula has to be modified. So we will discuss in the next chapter that one. The next concept is, what is the divergence of the magnetic field? Let us discuss in detail here. The divergence of any magnetic field. Here magnetic induction field strength we are considering. Therefore, the divergence of B bar is given by divergence of B bar equal the flux of B bar through surface S, which is enclosing the volume V, by volume V in the limit as V tends to 0. So the flux through surface S per unit volume is nothing but divergence of B bar, where we consider the very small volume, that is V tends to 0. So from this you can write 1 by V limit V tends to 0, that is very small volume, surface integral B bar dot ds bar. The flux of B bar through S through surface S can be written as surface integral B bar dot ds bar, equation 1. But we know that the magnetic lines of force are closed curves. Therefore, the magnetic flux over any closed surface in the magnetic field is always 0. Hence, as per the Gauss law in magnetostatics, just we discussed earlier, magnetic flux is equal closed integral B bar dot ds bar equals to 0. Okay, this is equation 2. From equation 1 and 2, you can write divergence of B bar equal del bar dot B bar that equals to 0. Therefore, the divergence of magnetic induction field strength is always 0. Del bar dot B bar equals to 0. Right. So, in another words, you can express that del bar dot B bar equals to 0 whether the point lies outside or inside the current loop. Thus, the divergence of magnetic field vector is 0 everywhere. If you consider the current carrying loop, if you consider the point either inside of the loop or outside of the loop, at every point magnetic field divergence always equals to 0. Del bar dot B bar equals to 0. Del bar cross B bar equals to 0 inside at the point inside the loop, but outside the current loop, del bar cross B bar not equals to 0. That should be equal to mu naught into J in the case of steady currents. But del bar dot B bar equals to 0, del bar cross B bar equal to 0. For the point lies inside the current loop. You remember that point. So what is the significance? Let me repeat. When del dot B bar equals to 0, that is divergence of B bar equal to 0, always at all points, whether inside or outside the current loop. The second one, this equation indicates that isolated monopoles do not exist. Therefore, there are no free north and no free south poles in the nature. But in the case of electrostatics, there we discussed that separate positive charge, separate negative charge are existing. But in the case of magnetism, no free north pole, no free south pole exists. Always both the north and south pole exist together. Monopoles do not exist. So they exist in pairs. Okay. The next concept is the curl of magnetic field vector B bar. According to Ampere's law, the work done in moving a unit north pole around any arbitrary shaped closed loop is equal to mu naught times to the flow of current in the loop. So this is the statement of Ampere's law. So we express mathematically it as closed integral B bar dot dl bar is equal mu naught into I. So when you consider a straight conductor, so around that you imagine any arbitrary shaped closed curve, right? The work done in moving a unit north pole along that closed curve, along the boundary of that closed curve is equal to mu naught times to the current enclosed by that closed loop. We express integral method as closed integral B bar dot dl bar equal mu naught into I. This is equation 1. You remember that this formula is applicable only for steady currents. In this chapter, we discussed only about the steady currents, magnetic field effects for the steady currents. But from Stokes' theorem, we know that the Stokes' theorem relates both the line integral and surface integral. So closed integral B bar dot dl bar can be written as that equal surface integral of curl B bar. Curl B bar nothing but del bar cross B bar dot ds bar. We studied in mechanics first sem. Closed integral B bar dot dl bar equal surface integral curl B bar, that is del bar cross B bar dot ds bar. Equation 2. Okay. So if di is the current in the elemental area ds, if that whatever we consider the closed surface, just imagine that that closed surface area is divided into small area elements ds bar. Then if di is the current through the small area element ds bar, you can write di equal to j bar dot ds bar. Current density j bar equals to what? J bar equal to current flowing through current flowing through unit area normally through the conductor. J bar equal to I by A. So from that, di equal to, this is the dot product of J bar and ds bar. J bar and ds bar. Okay. So now I is called integral of di, that equals surface integral, but di equal we substituted J bar dot ds bar. Okay. Substituting this in the above equation, then surface integral del bar cross b bar dot ds bar equal mu naught into surface integral j bar dot ds bar. Since the surface under consideration is arbitrary, you can write del bar cross b bar equal mu naught into j. So the curl of b bar equal to mu naught times to the current density vector j bar. This is applicable for only steady currents, not varying currents. You should remember that. For the steady currents, the curl of magnetic induction field strength del bar cross b bar is equal mu naught into j. Okay. What is the significance of the curl of wave? Since j bar equals to 0 for all points inside the current loop, then del bar cross b bar equal mu naught into 0. You will get del bar cross b bar equal to 0. So for the point lies inside the current loop, the curl of b bar is always equal to 0. For the points outside a current loop, then this formula is applicable. There exists curl del bar cross b bar equal mu naught into j bar. This is also known as Ampere's law in differential form. So closed integral b bar dot dl bar equal to mu naught I. From that we started our derivation. That is called Ampere's circuital law, integral form. Integral form, Ampere's formula. Del bar cross b bar equal mu naught into j bar. It is also called as differential form of Ampere's law. You can prove that del bar dot b bar equals to 0 using Boit-Savart's law. How? According to Boit-Savart's law, when the current is flowing through a infinite length of the conductor, then magnetic induction field strength due to the small current element dl bar at the distance r from it is given by db bar equal to mu naught I by 4 pi dl bar cross dr bar by rq, where dr bar is the position vector of that point where we are talking about the magnetic field strength. Okay. So dr bar is the position vector of that one. Magnetic induction due to the small element dl or due to the small current element idl is db bar equal mu naught I by 4 pi into dl bar cross dr bar by rq. Since r bar is the position vector of the observation point P, for simplicity, let us write db bar with b. So by replacing the db bar by b bar, so that b bar equal mu naught I by 4 pi dl bar cross r bar by rq, where r bar is the position vector of that point where the magnetic field is b bar. Now we have to prove del bar dot b bar equals to 0. Therefore, you consider del bar dot b bar, that is divergence of b bar, equal to del bar dot b bar equal to this value I am writing here. Okay. So that equals to mu naught I by 4 pi del bar dot dl bar cross r bar by rq. Okay. Yes. But the divergence of the cross product of two vectors a bar b bar, how we write? So from scalar triple product, del bar dot a bar cross b bar formula, we have b bar dot del bar cross a bar minus a bar dot del bar cross b bar. In this, you substitute a equal to dl bar, b bar equal r bar by rq. A bar equal to dl bar, b bar equal r bar by rq. So then you will write del bar dot dl bar cross r bar by rq equal to, from the above formula, R bar by R cube dot del bar cross dl bar minus dl bar dot del bar cross R bar by R cube. But here in the first term del bar dot dl bar that equals to 0. Curl of dl bar equals to 0. Then you will have right side only minus dl bar dot del bar cross R bar by R cube. So coming to the next slide, we are writing that one. First let us simplify that term. Del bar dot dl bar cross R bar by R cube equal minus dl bar dot del bar cross R bar by R cube. So then del bar dot b bar equals to what? Mu naught I by 4 pi dl bar dot. So this is substituted here. So del bar, this value substituted here. Again, let us simplify this term. The curl of R bar by R cube. Del bar cross R bar by R cube, you can simplify using this formula, using this determinant method. I, J, K, del bar components dou by dou x, dou by dou y, dou by dou z, R bar by R cube components. Since R bar by R cube is what? Xi cap by R cube plus Yj cap by R cube plus Zk cap by R cube, where R equal root of x square plus y square plus z square, because R bar is the position vector that equal xi plus yj plus zk, then modulus of R that equals small r equal to x square plus y square plus z square whole power of, so that is substituted here. So on simplification, you will get here I cap into, this is dou by dou x, not that, dou by dou y. Dou by dou y of j by z by r cube minus dou by dou z of y by r cube plus j cap into dou by dou z of x by r cube minus dou by dou x of z by r cube plus k cap into dou by dou x of y by r cube minus dou by dou y of x by r cube. Okay, so here printing mistake, it is dou by dou y. We'll get, so with the partial differentiation, where you consider r equal x square plus y square plus z square whole power of, we'll get I cap into minus 3zy by r power 5 plus 3zy by r power 5 plus j cap into minus 3zx by r power 5 plus 3zx by r power 5 plus k cap into minus 3x by r power 5 plus 3x5 by r power 5. All the terms gets cancelled, equal to 0. So since del bar cross R bar by R cube equal to 0, so finally we get del bar cross del bar dot B bar equals to 0. So in this way, we can prove the divergence of B bar equal to 0 using the Boit-Savart's law. So what is its physical meaning? So there we consider the where there dB bar is replaced by B bar. Since the magnetic field due to the entire circuit is the vector sum of fields due to the current elements, therefore the divergence of the magnetic field is always 0, right? So on comparing the relation del bar dot B bar equals to 0 with del bar dot E bar equal rho by epsilon naught. So this is, we have the formula in magnetostatics. That is nothing but Gauss law in magnetostatics. In electrostatics, we have the Gauss law del bar dot E bar equal rho by epsilon naught. Comparing these two equations, it is very clear that in the case of magnetism, there is no term of rho. That means what? So that means there is no magnetic energy density. So we conclude that magnetic charge density is 0, or that means there do not exist isolated single magnetic poles, or in other words, there do not exist either free north pole or free south pole in the nature. Okay. Now, the comparison between electrostatic field and magnetic field, right? So the source of electric field is the charge, either stationary or in motion. Means what? If the charge is at rest or if the charge is moving, electrostatic field exists. The source of magnetic field is a steady current or a moving charge. For example, if the current is flowing through the conductor, so the steady current, due to the steady current, the magnetic field arises around the conductor. The current flowing through the conductor is nothing but the moving of electron charge. Therefore, the source for the magnetic field is a steady current or a moving charge here. Electrostatic field is the conservative field. Therefore, del bar dot E bar equals to 0. When the divergence of a vector equal to 0, that vector is said to be, the vector is said to be solenoidal vector. Here del bar dot E bar equals to 0. Then E bar can be expressed as the negative gradient of a scalar potential, that is electric potential. E bar equal minus grad V or minus del bar V. But whereas in the case of magnetic field, it is non-conservative. Therefore, del bar dot B bar is not equal to del bar dot B bar. Since it is a conservative force, here what we are writing, not del bar dot E bar, sorry, correction this one, del bar cross E bar equal to 0. So then A bar is called as what? A rotational vector, and the E bar is said to be conservative field. Then E bar can be expressed as negative gradient of a scalar potential. Hence, we got the relation E bar equal minus grad V electric potential. Here, del bar cross B bar, it is not dot, del bar cross B bar equal to mu naught C. Del bar cross B bar is not equals to 0. Therefore, it is non-conservative. Right. So here the magnetic field can be expressed as the gradient of a scalar potential at points where electric current exists. So magnetic field cannot be expressed as gradient of a scalar potential. Here electric field can be expressed as the potential, gradient of the potential, but since B bar cannot be expressed as gradient of the potential, it is the non-conservative force. Electric lines of force are open curves. The magnetic lines of force are closed curves. So there exist positive and negative charges separately, but here free north pole, free south pole do not exist. Here individual charges, either positive or negative charges exist in the nature. Here monopoles do not exist in the nature. Here del bar dot B bar equals to 0. Del bar dot B bar equals to 0. Here del bar dot B bar equals to 0 in the case of magnetic field. In the case of magnetic field, but here del bar dot E bar equal rho by epsilon naught. Here del bar cross B bar, del bar cross B bar equals to what? Del bar cross B bar equal to, not equals to 0. Del bar cross B bar equal to mu naught J. So we correct this one. Del bar cross B bar equal to mu naught J here. Here del bar cross B bar equal to mu naught J. Okay. Here the correction is del bar cross E bar equals to 0. Del bar cross E bar equals to 0. So the summary of this present lecture are, first we define the magnetic induction field strength. After that we have seen the properties of field vector. We define the magnetic induction field strength from different formulas. B equal to FB by Q naught V sin theta. From the form F equal to ILB, B equal to FB by IL for theta equal 90 degrees. In terms of magnetic lines of force, B equal to flux density, that equal magnetic flux by area. Okay, and also we defined B in terms of FB by M, that is force experienced by a unit north pole placed in the magnetic field. Okay, monopoles do not exist in the nature. Mathematically, we express it as divergence of B bar equal to 0 or del dot B bar equal to 0. For steady currents, the curl of B bar is always equal mu naught into J bar. This is known as Ampere's differential formula. Thank you. Oh, right.